Any questions? So let me give you now an example of how this works. Just to make it simple, I'm going to use not an outer loop but an inner loop. And think of it as a single input, single output system, okay, just to make it a little simpler. And the reference model for the command filter will look like this. Let's do it this way. It has to go here. And using enough space. Reference model or command filter. IP. Call this KU. Then we want this XM, X. Okay. How is this different from what I have just explained? What I had just explained was Ku is equal to 0 and Km is equal to 1, right? That's how I explained it to you. In that case, it would be RP, command filter, right? Plus, minus, x plus u, x. Okay, right? So, how is this different from that? The difference is this. Ku is equal to 0, Km is equal to 1, so it would be exactly the same thing if I do it this way. Alright? But just to make it a little generic, so you have a little bit more design freedom, I keep it as Km and Ku. Okay? And do the manipulations accordingly, but whatever I do in terms of manipulations, if you said Ku is equal to 0, Km is equal to 1, you would immediately obtain this one. Okay? The bottom line is the output of the reference model, I call it Xm, should be equal to X, so I'm trying to follow that X interface. Okay, this is the error. I'm looking at the error. I'm trying to make sure that that error goes to 0. So that's what I'm talking about. Okay, we said the reference model is called the command filter. It's also called the low pass filter. It filters out the high pass, high frequency content. So what does a reference model look like? A simple reference model. A simple one. It would look like this. It would look like xm dot equal to, this is what I use here, am xm plus bm times rt. This is reference. So, what does this mean? What does it mean? It means this. Time, xm, you have an input rp, okay, and xm is the output. Xm is the input, you have an rp as an input. I shouldn't be doing that. xm should be doing this. Okay. If it's a single bit, single output system, like I did for the outer loop, it will look like this. So xm should go like this, and rp should be the input. And am and bm is our design. So we are going to choose am, b, and bn in such a way that if you give a step input, it will respond like this. Okay? In a practical sense, in your homework or something, if it's a single input, single output system, the way we did it previously, you can use a first order system like this, where x is a real number. Okay? And a and b are constants, so it will be a first order system. And believe it or not, this one will give you a smooth input like that. And I can try this in MATLAB. And you can try this in MATLAB and see how it works. Okay? In fact, if you take this one, if this is a single bit, single output system, okay, and if you take the Laplace transform of this, it will look like this, assuming that it starts from 0, as x is equal to a times x plus b times rp, okay, taking the Laplace transform, you would get s minus a times x is equal to b times rp, okay? And the transfer function would be rp b divided by s minus a, right? If you take this first order system and you write it like that, take a Laplace transform. You obtain this, right? S times x is equal to a times x plus b times rp. Move this to the other side, you get s minus a times x, b times rp, and this will become x divided by rp, right? b divided by s minus a. So this is your transfer function. So your transfer function here, and you can use a transfer function like this in MATLAB. Okay. There's something called transfer functions. Okay. And where's the root of this one? Where's the eigenvalue? It's here, s minus a. Right? The eigenvalue is at plus a. That's where the characteristic equation of your filter is at s minus a is equal to 0 is the characteristic equation, and s is equal to a would be the eigenvalue of your filter. So what I'm trying to say is that if you had a single input, single output system, you could actually use this as a transfer function in Simulink. You just use a block for a transfer function in Simulink instead of the reference model. And the transfer function can simply look like this. And this is a first order filter that looks like that. Do you see what I'm saying? So if you take the map, maybe this is a Wednesday. We could do an extra class this Wednesday too. Is that okay? Okay, let's do it this Wednesday. Okay? So I will show you how I do this in MATLAB Simulink. If I have time, I'll do it today. Okay? Let's decide at the end of this. Let's do it this way. Let's have it this Wednesday, no matter what. Our class. Okay? 11:40 this Wednesday. So we have time. Is that okay? Good. And then we can have a New Year's celebration. Okay, so this Wednesday then, okay? So this would be a first order system that we can add here. In this case, I'm making it a little bit more generic where you have more states than just simply one. If you just have simply one, you could use a transfer function instead of the filter. But let's make it more generic. Let's say this is a reference model that we would like to follow. The output of XM, you give an input RP, right? And the output of this system would be, it is a differential equation, but the output will be XM. So hopefully it will look like this for a step input RP. And then what you want is that the error goes to 0, which means X will follow XM. That's what you want. The goal is that EN goes to 0, which means X matches XM. That's what we want. Okay? And you are going to design this part such that this will match that. And of course you also design K. But we design K first and then we design the rest. What do you design here really? You choose AM, BM, and then you choose KM and KU. And if you just want to do this, you simply choose KM1 and KU0 and it will look like that. Okay? So how are we going to do that? The goal again is to make sure that X goes to XM, the output of the reference model, and therefore the error goes to 0. That's the goal. Understood? And we are designing AM, BM, KU, and KM. We are going to choose them. It has nothing to do with A and B of the real system. Understood that? Any questions up to this point? Because after that it's mathematics, and then we will see how to calculate this. But it's more important that you understand what we are trying to do. Yes.
William, what is the sign of the branch coming from KU?
Plus. It actually doesn't matter since I'm choosing it. If it's minus, then I choose a minus over here. Okay. What does it do? What is KM and KU? It balances. Let me talk a little bit about these things. It balances. Sometimes you just want to have a feed forward term. We call it a feed forward, which means before it goes to this, you first want to have an initial input to the system, even if it's not much. But you know you're going to go there, so you want to have an initial input to your system. What does it mean? Let's say you want to speed up your airplane, okay? And you know you want to do it smoothly, slowly. But you know from the very beginning that you need to put in more fuel into your engine. So you just send a little bit of a signal up front so that immediately starts putting fuel into your system, because you know the response of the engine will be slow and all that. So some of that input you might still want to send in ahead of time. This is what we call a feed forward. Okay, this is a feed forward. I'm talking this one here. Okay, so it's a feed forward. First of all, before you even go there, just send ahead of time some of the signal into the device. And here you can schedule, or you can scale what comes out of the reference input. Very often this is equal to 1. I can't remember this one being anything else than 1. I think in all the controllers I ever designed, this was probably mostly 1, and sometimes I have a feed-forward term on top of this. Okay. As I said, this requires a little bit of experience, of course. Therefore, you need to play with your Simulink models. Okay, play with Simulink if you want to master this. It requires some experience. That's why we call this design. Okay, we are designing a control system. It's like designing an airplane. Okay, if someone comes up to you and says, "How do you design an airplane?" Well, of course, there are some methods, but there's not one way of designing airplanes, right? Some companies do better jobs in designing the airplane. Some companies don't do a good job in designing airplanes. Both fly, the other one flies better, and all that. It's a design problem. It's the same thing over here. Again, designing control systems. There's not one way of designing a control system. You can remove the reference filters, you can remove the feed-forward terms, and maybe play with this one. Or you do an auto loop, or you do an integral controller, and then you don't need a reference input. Or you do it always, it's a design of the architecture. It depends on the problem, it depends on your capability, it depends also how much you have experience. If you design a controller for an airplane, if you do it 2 times, 3 times, the 4th time you kind of know what the problems are, and you do it better. But there's no one single way to design a controller. That's why we call it control system design. It's a design problem. Okay? Sometimes students always ask me, okay, so I'm going to do this, check. I'm going to do this, check. I'm going to do this, check. And then I'm going to have a perfect result, right? No. You're going to design. There's not one single way of doing this. I'm just giving you the tools and you're the designer. These are tools for you to design a good control system. Does that make sense? Okay. So therefore you need to know what you're doing. And I told you there's no such thing as a cookbook. Cookbook, you know what that means, right? When you have a book and you cook, it says 2 eggs, a little bit of milk, and then stir, and then butter, wait 5 seconds, 5 minutes, put it in the oven, and in 2 hours, take it out, and then it doesn't taste good. What your mom does, it tastes always better, right? So, there's no such thing as a cookbook for this either. You can do it in many different ways. And it requires experience. And you need to understand what you are doing. When you make a cake, what does an egg do? What will happen if you put more eggs in there? Or if you don't know, it doesn't matter. Well, I don't know. So for me, it doesn't matter if you say 1 egg, 3 eggs, 5 eggs. I don't know what they do, what it does. But here you need to understand what each of these pieces are actually doing. And then you get a feel for it, and then you play around. Okay? So anyway, too much talking. So that's your reference model. RP, that's your reference model. The actual open loop model is x dot is equal to ax plus bu. Open loop dynamics. And then u, that's u. That's u. U equal to minus kx plus km xm plus rp xu. I have a feed-forward term, I have the output of the command filter, and I have a feedback gain k. All right. So when you choose this, when you first design this is the reference model. Well, I can tell you the first few requirements. The first one is you want to choose AM such that AM is stable. I mean, it would be silly to choose an AM, a matrix over here, that makes this thing unstable, right? Stupid, right? I mean, divergent at least. If you would choose a divergent reference model, which means you give a step input and this one goes to infinity. That would be stupid, right? You don't want that. So you want AM to be stable, that's for sure. Okay? Number one. You want AM, BM controllable. I mean, you're choosing them, so choose them controllable, A and BM. And AM must be stable. Okay. So that's that. I thought that they were, this is obvious, but alright. So AN is x minus xn. Okay. And if you take the derivative of both sides, you get AN dot is equal to x dot minus xn dot. Right? Obviously, take the derivative of both sides, and you redefine this. I mean, it's not really part of the controller. We just have this in order to make sure that we have it in our equations and the n goes to b. Let's call this one 2 and this one equation 1. Okay. Subtract 2 from 1. And get xm minus x and xm minus x plus so trying to solve them together. So this one here, so right here is minus en dot is equal to times u is here. Plus rp. This is Ku here. Or this one here. This one here. It's not xu, there's no sign to xu. So let's do some manipulation over here. That is equal to x. And this one here becomes so it's a minus here. That is nice. Okay. So wait. Sorry, this goes on. almost done, so bear with me. That's to change the signs here. This I can make this plus, minus, and minus 1. Let's call this one y. And let's call the rest here z. Let's switch opposites. So let's call this one. Actually, it doesn't matter.
This is minus beta.
Excuse me?
So draw AM minus beta. We have 2 times.
This one?
Yes.
No. I have 2 times because they will cancel. But I add them in order to obtain this En. So I'm adding and subtracting the same thing in order to obtain this. It's just an extra trick, yes. Because we don't have it over here. We don't have it over here. We don't have it over here. It's just what he's asking is what are these 2 things? I'm adding this, subtracting that, and this is 0. I'm just adding this in order to obtain En. So, this one is simply En dot is equal to term Z, which is a matrix, times N minus Y. And Y is another matrix. I mean, it's big, but it's simply that. So, what do we want? I'll do this right, just give me a second. Okay. All right, so this is here the result. En dot is equal to 0. So we want, what do we want? We want En to go to 0 as time goes to infinity, right? So that's what we want. How can I achieve that? How can I achieve that En goes to 0 as time goes to infinity? It's actually quite simple. What do I need to have? What should Z be like? Should it be, what should be the property of Z in order for this to happen? Eigenvalues should be all on the negative side, so it should be a stable matrix. We call it Hurwitz. Okay? Stable matrix. Okay? Hurwitz matrix, where all eigenvalues are on the left hand side. So we want this equation to be a stable equation, so therefore Z should be chosen such that the system is asymptotically stable. Totally. Because it's a linear system, I mean, stable, it's already asymptotically stable. So Z should be asymptotically stable. We call it Z is Hurwitz. That's another terminology that I want you to learn. A matrix that has all eigenvalues on the negative side, we call it a Hurwitz matrix. Okay? Because a matrix is not really stable or unstable. I mean, an equation can be stable, right? A differential equation can be stable or unstable. But the matrix itself is not really stable. You know what I mean when I say stable, but that's not really a good terminology because the matrix by itself is not really stable. It has all eigenvalues on the negative side. Okay? We call it a Hurwitz matrix. So that's that. So that's T. What else do we want? We want y to be equal to 0 because if y is not equal to 0, it will just keep moving with En, right? It will just keep playing with En. As y is changing, En will also change. It will be like an input to the system. Y is like an input to the system. We want y to be equal to 0, no input, and we want z to be Hurwitz so that En goes to 0 as time goes to infinity. That's what we want. If En goes to 0, then xm is equal to x, and that's exactly what we want. Right? Do you understand that or not? Good. So, y should be equal to 0, and z should be Hurwitz. So, let's write down the rules then. Let's write it. Maybe I write it here. Because y is like an input to this differential equation. It's like an input. Isn't it like an input? It's like x dot is equal to ax plus bu. U is the input. As u is changing, x will move. If you don't give an input, x dot is equal to ax, then no matter where x will start, as long as a is Hurwitz, x will always go to 0. And we want En to go to 0. But if you have u, an input, you keep playing with x. So we want En to go to 0. So therefore, I want y to be 0. I don't want an input in my differential equation. This is what we call the error dynamics, right? Error dynamics. It's the dynamics of the error. So we want that error dynamics not to have an input. Understood? Okay, so rule number 1. Now, how do we choose now A, B, KU, and KM? So, rule number 1. AM is stable. I don't like to call AM stable. I should call it Hurwitz, but I'm afraid that you won't understand it. Okay. AM is stable. That was the first rule. I mean, you can't really run it. Rule number 2. AM BK. AM minus KM is stable. So Z is asymptotically stable. So Z is Hurwitz. Okay. So that this equation becomes asymptotically stable. So Z is equal to that, and that should be asymptotically. That should be Hurwitz. So that's rule number 2. Rule number 3, and this is coming from Z, and rule number 3. That is for y is equal to 0. That's that rule. And here you can do a number of things. If you do that, then it will cancel. Right? Okay, this one here, AM minus BKM, if that's equal to that, they will cancel. That's one. The second one is BKU equal to that's it. If you do that, then you're fine. So, what do we do? This is a little cookbook. And I say, don't use it. Okay? It's a cookbook and don't use it. Well, but take it as a guide, you know. First, design K. First design K. I mean, that's the feedback gain K. Design it the way we learned it. Use Bascura, use LQR, whatever. Just design K. 2. Select KM and A. So this is what I recommend. Let's not use it. Don't say that. I mean, it's a recommendation. So I recommend you do this. First design K. That's your feedback in K. Select KM and AM, because now you have the freedom to select AM and KM, but make sure that this turns out to be stable, okay? You can choose these two. So if you choose KM equals to 1, you want to make sure that AM minus B is also equivalent. Second thing, select BM, now here, and find KU. Okay? And from here, you know AM, this should also hold. How do you get that? AM minus A is equal to B minus AM. So they have to hold together. They have to hold together. So you choose maybe AM and then do that, or choose KM and then make sure that these two hold together. They have to hold together, of course. When you choose KM and BM, KM and AM, it has to hold together over here. Then select BM or KM. So this is how you do that. Now, of course, this becomes a little bit complicated because we are looking at states here. I have a number of states over here, number of states over here, so we are looking at mean, and this is a vector and all that. Of course, it becomes a lot simpler when you use the reference model not as into the states, but if you use it as an outlook, as a single output system, this whole thing becomes, of course, a lot simpler. What I'm trying to say is, if you would be choosing, the way I explained it before, you have a reference model. Use something like this, then the reference model in YC, let's say, is only one number. Okay? If YC is only one number, then your system will simply be ym dot is equal to y times 1 plus E times RP. Then all you need to do is really choose A and B, right? And you can immediately say Km is equal to 1 and Ku is equal to 0. So this is a much simpler problem. Okay? A and B are real numbers. So all you need to do in this case is just to choose A and B, two numbers, and you can immediately say Km is equal to 1 and K is equal to 0, but still make sure that some of these conditions hold. Okay? So this is a much simpler problem. But if you want to be more generic, then these are the rules, because now you're choosing a reference model that's actually not where xm is a vector, and you have these weights and the feed-forward terms, and this is a more generic case, and the design becomes a little bit more difficult. But in most cases, in your project and so on and so forth, I think all you need is this. Okay, an extra. At most, you might need this. Okay, like a feed-forward term. This might be the most that you will need in your project. And I would not recommend to put the reference filter over here, somewhere here. I would put the reference model all the way to the out, where you have your reference inputs and the reference model. So if you do that, then you have the problem becomes a lot simpler, where A and B are real numbers, and that's all you need to choose, and maybe a number Ku. But this should still hold, of course, because this is the most generic form, right? This is for a larger number of states. Does that make sense? Do you understand what I'm trying to do, where things are coming from? Is that okay? Any questions? Yes.
For an airplane, the A matrix is an 8 by 8 matrix, right?
Yes, but you usually don't want to use all 8 states in one controller.
I would ask, how am I going to choose those 64 values for my reference model?
Exactly. So it's very difficult to do. So I've never seen anywhere somebody designing a reference model for 8 states. Okay? That's number one. Number two, an airplane, rigid body modes for an airplane have 8 states. That's right. However, if you design for an airplane, you would like to separate the controller, the longitudinal controller, from the lateral controller. Because even in flight mechanics, we said they don't affect, the coupling is not too high on an airplane. So let's remove them and let's say separate them and design a controller for the longitudinal controller dynamics and a controller for the lateral dynamics. So now we are talking 4 states and 4 states. 2 separate controllers, independent. One is controlling this, the other one is controlling this. And they run at the same time. Okay? So 4 states for one, 4 states for the other. That would be the inner loop. Okay? If you want to have a reference, a controller, a reference model for these 4 states, then yes, this has to be 4 by 4, and you're still talking 16 numbers. Okay? And I would never do that. I would be doing this. Okay? And then I would ask you, what do you want to control? Velocity, angular rate, what do you want to control? Let's say you tell me you want to control angular rate. So the pilot will have the pilot stick, and this one will control the angular rate. Okay? So, angular rate, I will put another outer loop here, put the angular rate, and now I have a single input, single output system. I'll put the reference model to angular rate. 4 states, 1 stabilizing loop for those 4 states, for the lateral or the longitudinal. Separate what you want to control on the axis, because the pilot has really one axis to control. One axis here, one axis here. That's it. So question is, what will the pilot control with this? Angular rate, angle, velocity, what? What we usually control is the angular rate, for instance. You do this, you get a rate. You do this, slow down the rate. Rate, or angle. You do this, control the angle. Put it back, put this. Okay? Put this, and do this. Do that. So you want to climb, do that, increase throttle, and you go up. Reduce throttle, reduce your angle, go back to steady. Okay. So the pilot here is sitting here, really just controlling the angle. What happens to the other states? Well, the other states do whatever they do. I mean, if you do this and you do pitch up, you don't change the throttle, you will slow down, right? You know that. Go nose up, angle of attack increase, you get drag, you first go up and then you slow down. Okay? But the pilot is controlling the angle. You could say the pilot is now controlling the angular rate. You can do that too. So you do this, you get the rate, put it back to zero, you will try to stay there. Of course, the helicopter, the airplane cannot. It will probably slow down because of the drag. And if it will start falling down, it would be a stupid thing for the pilot to do. Nose up and no throttle. Right? What you do is you get nose up, increase throttle, and then you have a steady flight or whatever. How are you designing control? I don't know. But this is what we call a control system design. What will the pilot control? It has only two axes. So there has to be one number. You cannot tell the pilot to control all 5 systems. You cannot say, I have 8 states over here, and the pilot will control all 8 states. How is he going to do that? I mean, let's say you have, as you said, let's say I'm controlling, I have 8 states, and I have 8 states to get in, and therefore I need an RP that is 8. How is the pilot going to do that? Going to give an input to all 8 states? No, he's going to get to 1. So your job is to make his life easier. So typically I would stabilize the system, and I would have one variable that the pilot will control in one axis. And there I will put the reference model. And then I only have to choose A. Yes, please.
Is it possible to further reduce the lateral or longitudinal dynamics into 2 sections?
Of course. The question is, rigid body mode 4x4, right? 4 for the lateral, 4 for the longitudinal. Is it possible to say, I'm going to not use 2 equations, just these 2 equations? Yes, you could. That means the following. I don't care about these 2 equations, I will just look at these 2 equations. With these 2 equations, they can do whatever they want.
And it is physically meaningful.
It must be physically meaningful. For example, remember in flight dynamics we had for the longitudinal mode, we had the phygoid mode and we had the short period mode. Let's say you just want to have a feedback controller that will reduce the phygoid mode. And the short period mode, I don't care because it's not that horrible. It dies out very quickly anyway. So the short period mode, my controller, I don't care. Let the airplane do whatever it does. All I care is the phygoid mode. Well, if you remember in flight mechanics, we had an estimation for the phygoid mode. It was only 2 equations. Right? We used 2 of the equations in order to estimate the phygoid mode. Now, if you're only interested in designing a control, stabilizing the phygoid mode, you just take those 2 equations, design feedback gain K, don't even tell the pilot anything, and you just stabilize the phygoid mode with these 2 equations. What happens to the short period mode? Whatever it does, it does. Okay? What happens to the lateral mode? If you don't have a controller, they do whatever they do. There will be lateral, there will be spiral, whatever. So you will have a controller that will only stabilize or manipulate, let's say, the phygoid mode. In that case, your state matrix can only be 2 lines.
A and B.
Yeah, the A will be 2 by 2. B will be 2 by 1, I guess. If you want to do it with the elevator. That's why I call this a control system design. You are the designer. You look at the airplane. You look at the phygoid mode, you look at the short period. If the short period mode is not too bad, if you say, I don't want to touch it too much, it's okay. Just take the phygoid and design a control for the phygoid. If you don't like the short period mode, take all 4 and design it for all 4 of them. You see? For example, for a helicopter, to go back to your question, for a helicopter, the longitudinal and the lateral modes, they are not really uncoupled. They are coupled, which means you need to look at the 8x8, which becomes quite difficult. Then you make some intelligent decisions. Oftentimes we say, let's just use, because 8x8, it's very difficult to design and control. Let's just use P dot, Q dot, R dot, the PQR equations, just 3 lines. They are in all 3 axes, right? P, Q, and R, all 3 axes. Let's just use P dot, Q dot, R dot as my linear system. Forget about the rest. Let's just stabilize PQR. Very intelligent decision to make. You have now a 3x3, and you are looking at all 3 axes. You are not doing everything together, but you have to be careful and know what you're doing, because you are only looking at P dot, Q dot, R dot, and your velocities, they can do whatever they want. But intelligently, you might think, well, in order to get velocities, you need angles. I mean, if you don't have angle, you don't have velocity. All right? You need angles. Okay? So, how do angles happen? Well, angles come if you have PQR. So, if you can control PQR, you will control angles. And if you can control angles, you will control velocities. So, you might say, forget about velocities, forget about angles. Let's just control PQ and R. Therefore, choose X, the states, as PQ and R. So you have only a 3x3, a 3-dimensional system. That's what I call a control system design. There is not one way to do these things. You need to understand your aircraft, meaning that you need to know the non-dimensional equations. You need to be able to linearize it, look at the eigenvalues, and then make intelligent decisions how you want to design your architecture. And then you want to ask, what should the pilot be controlling? If it's a passenger airplane, maybe you want to control just altitudes and velocities and heading. That's it. Just the heading, just the altitude, just the velocity. So design a controller where the pilot just have 3 knobs: altitude, velocity, and heading. That's it. So how do you design a control system that takes the airplane to those 3 inputs and slowly moves it there? For a fighter airplane, it's of course different. The pilot wants to do a lot of maneuvers. So maybe you just want to control the angular velocities. Or if you want to do a missile, let's say, you just want to track a certain trajectory. So all I care is, am I on the right XYZ position? So you just want to control position. So design a control system so you can track the position. There's not one way of doing this. Okay?
I couldn't understand. How can we achieve this without solving 6 difficulties?
At the end, the aircraft will be represented by 6 of equations. Your controller, when you design your controller, you only look at 3 equations. So you design these K matrices based on these reduced number of equations, and hope that it will work for the full system. But when I reduce them I do it intelligently. I don't do it just stupidly. That's why aerospace engineers need to do these control systems. They need to understand what's going on with the aircraft. Anyone can design control, I mean not anyone, but there are a lot of disciplines that design control systems. But if you don't understand the aircraft, you cannot design a control system for the aircraft. You first have to understand the aircraft. And that's why aerospace engineers need to do that. Okay? So, as I said, as I gave you the example, you have an 8x8, and you say, I'm only interested in the figoid. Alright, so I know it's a fixed wing airplane, I know I can separate the longitudinal and the lateral, so take the 4x4 for the longitudinal. I just want to do the figoid, okay, let's take the 2. So I have the 2x2. So I design everything based on the figoid. But then I still take the controller and put it into the full nonlinear system, and then hope it works. If you do it intelligently, it will work. It will just reduce the figoid load. And everything else, it will not. It will touch it a little bit, but there will be not much effect. No, I'm talking about the whole control design. Talking about control design. And then the reference model, that's up to you. I told you what the reference model is doing. Use it as you want. As I said, I'm just giving you the tools. And you have the freedom in your project to use those tools the way you want. Okay? And I'm here to help. You ask me questions, I will come back and help. This might be your first controller design, it might not be the best, but you do at least one. Okay? Any other questions? So let's do a 5-minute break. I'll bring my computer.